Welcome experts to today's technical restoration project. Starting in a wild banana grove, a setting completely alien to technological devices, he is beginning his search journey, venturing deep into a massive scrapyard. The wet and muddy environment is the nemesis of electronic circuits. Extremely harsh conditions with toxic smoke rising, heat, and humidity from underground burning trash piles. The visual inspection process begins amidst the scrap heap. The goal is to search for abandoned electronic components. Visibility is restricted by white smoke and mixed waste. Requiring extremely sharp observation, he has spotted the first target on the ground. A device lying hidden beneath a layer of garbage. Surprisingly, it's a Sony Live View Remote RM LVR1, a signature remote control accessory of the Action Cam line. The entire surface is sealed by a layer of hard, dry mud. Checking the physical feedback of the rubber buttons, of course, there is no sign of life. He continues to scan the area where the remote was found. The second piece of the equipment set has been revealed, lying half submerged under the wet dirt and rocks. It is the body of the Sony FDR X1000V Action Cam, Sony's legendary high bitrate 4K recording camera. The polycarbonate shell has suffered severe environmental devastation. The standard water resistance capability has likely been compromised. The bottom part is heavily accumulated with sticky organic grime. The front Zeiss lens faces the risk of scratched coating. The device needs to be removed from the scrapyard for an in-depth diagnosis, which requires a sterile working environment. Preparing the workbench with basic tools, including a magnetic stainless steel tray, cleaning solutions, and wiping cloths. Equipping nitrile rubber gloves to prevent static electricity and chemical damage. He begins spraying the cleaning solution onto the remote, using a microfiber cloth to reduce friction on the LCD screen. As the congealed mud clings extremely stubbornly, applying strong mechanical force to thoroughly wipe the edges and corners. The button gaps are where the most mineral deposits accumulate. The back with the pogo pin charging contacts is also scrubbed. The oxidation process will increase contact resistance. Proceeding to test press the record and navigation buttons. The buttons still retain good physical travel, but the LCD panel shows absolutely no response, due to either a depleted battery or a short circuit. Shifting the cleaning focus to the FDR X1000V camera body. The solvent seeps into the crevices of the plastic shell, focusing on cleaning the mud around the mesh of the stereo microphone. Using a cloth to vigorously wipe the connecting grooves and battery cover, reddish-brown grime starts oozing out of the crevices. He sprays more wide-area cleaning solution to break down the structure of the grime. The original white surface of the Sony gradually reveals itself. The monochrome LCD screen on the side has become yellowed and mottled, a clear sign indicating that water has seeped past the rubber gasket. Trying to activate the physical power button, but it is useless. The power management IC or internal battery circuit is damaged. Checking the mechanical latch mechanism of the bottom battery door. It is very stiff and jammed. Starting the teardown procedure to disassemble the device, using a micro flathead screwdriver to remove the hinge of the I/O port cover. This area protects the micro USB port and external mic. Carefully lifting the cover out with pointed tweezers. Bright red rust covers the entire gold-plated copper contacts. Moisture and water have completely corroded this data interface cluster. Continuing to unscrew the plastic retaining tabs on the underside. Inserting tweezers to gently pry the rear seam to separate the retaining clips. Requiring meticulousness to avoid severing the fragile signal cables. Removing the plastic protective cover for the front lens cluster. Revealing the Zeiss Tessar lens cluster and the upper microphone circuit board. The stereo recording circuit has been heavily sulfated. Mud residues cling tightly to the waterproof rubber gasket of the lens. Separating the main polycarbonate protective shell from the internal chassis. Advancing deep into the area housing the motherboard and sensor. Prying open the battery compartment cover with metal tweezers. The No Problem BX1 lithium-ion battery has swollen severely. Using force to pry the tightly wedged battery out. The leaked chemicals have formed a patch of stark white salt. These two energy cores are completely dead. There's a risk of explosion if we try to recharge them. He removes the plastic casing holding the monochrome sub-display. The snap-fit mounts are stuck fast due to the packed mud. Using tweezers inserted into the groove to pry open the joint, the main PCB motherboard gradually reveals its surface. The condition of the printed circuit is extremely bad. Corrosion and rust stains are everywhere. The LCD screen is connected via an FPC cable. This thin membrane circuit is very fragile and easy to tear. Unscrewing the screws, securing the screen's steel protective frame, carefully wedging tweezers to lift the support base, peeling away the flat signal cables. The mud has penetrated right into the microcontroller. Using a high-temperature soldering iron to desolder, the soldering iron melts the solder at the positive terminals. Thermal energy breaks down the tin alloy bonds, successfully disconnecting the power supply line from the motherboard. Using a screwdriver to remove the motherboard mounting screws. The tiny screw heads are rusted. Detaching the battery contact assembly with its nickel-plated springs. The plastic compartment is covered in chemical foam from the battery. A close-up look at the microcircuit connection ports. The 3.5mm jack and the USB port are heavily rusted. Lifting the entire motherboard out of the chassis. Using tweezers to disconnect the peripheral module plugs. The underside of the motherboard is covered in white salt deposits. Electrolysis has completely destroyed the plating. Continuing to use the soldering iron to remove the microphone cable. Touching the soldering tip quickly to avoid thermal shock to the components. Completely detaching the tiny audio modules. Fully freeing the motherboard from the frame. Tweezers are used to pry out the contact springs. The metal has lost its elasticity due to severe oxidation, removing the conductive copper strips inside the walls of the plastic chassis. Now only an empty shell remains. Cutting off the remaining rotted wires. Separating the record button assembly with its LED indicator. Removing the monochrome LCD screen from its cover. Sorting all the components onto a stainless steel tray. We have a huge mess that needs cleaning. Preparing a tray with a specialized cleaning solution. Pouring water straight into the tray holding the dirty parts. Soaking the entire housing and motherboard in water. Using a bristle brush to scrub hard into every nook and cranny. Scrubbing away the red dirt stuck to the plastic surfaces. Carefully brushing the cooling vents and joints. The polycarbonate shell starts to regain its color. Scrubbing the inside of the side cover. The dirt dissolves, turning the tray of water completely murky. Detailed cleaning of the lens protector assembly. The brush bristles slip through the microphone recording holes. Processing the back cover, holding the directional buttons. Scrubbing off the most stubborn, calcified deposits. The riskiest step. Scrubbing the motherboard directly. Soapy water washes over the IX and capacitors. Scrubbing vigorously to remove the white sulfate salt layer. Being careful not to break off the microscopic SMD components. Washing the flexible FPC ribbon cables again. Cleaning the severely tarnished protective steel plate. The bristle brush repeatedly scrubs the aluminum surface. Only strong friction can remove the oxidation film. Cleaning the protective shield for the battery circuit. Thoroughly removing rust residues to prevent further corrosion. Using a brass bristle brush on the magnetic shield. The metal bristles scrub away the surface rust layer. Finishing up the cleaning of the other small modules. The cleaning solution has turned a thick gray color. Continuing to clean the accessory modules and small buttons, ensuring no mineral deposits are left behind. Moving on to the processing of the polycarbonate outer shell, the external protection. Removing the connection port covers. Using fine sandpaper to sand down the surface of the plastic shell. The physical friction smooths out the scratches. This operation aims to remove the old yellowed paint completely and clean off the oxidized surface, sanding evenly with steady hands to create the best adhesion for the restoration paint. This requires immense patience. Every curve and edge of the shell is handled extremely meticulously, preparing for the primer coat, pouring clean water to rinse off all the components that were just scrubbed, agitating them vigorously in the tray to thoroughly wash away all soap residue, and cleaning chemical deposits. Absolutely no chemicals can be left to stagnate. Pouring out the dirty water, ready to dry the mechanical parts and microcircuits. Visually inspecting the cleanliness again. Treating the rusted screws with a heated chemical solution. Immersing the metal completely into the boiling solvent. The chemical reaction produces smoke, stripping away the tightly bound iron oxide on every thread, restoring the original screw threads. Hanging the plastic shell on a rack for spray painting. To reconstruct the exterior surface, compressed air pushes the microscopic paint particles, spraying an even coat of white paint onto the waterproof casing, completely covering imperfections caused by impact. This paint layer will restore the glossy shine and enhance its durability. Waiting for the paint film to dry and set. Next, moving on to the stage of measuring electronic components with an analog multimeter. Inspecting the printed circuit board after water exposure. Using the 2 test probes to check continuity and impedance of the SMD capacitors. Identifying if the protection diodes are blown. This step confirms there is no short circuit. On the motherboards, VCC, ensuring safety before applying charging power. Wiping the contact surface of the FPC cable clean, using a thin microfiber cloth. Cleaning oxidation from the copper contact pins. Using tweezers to pick up the connection module, accurately aligning it into the slot. Starting the assembly of the intermediate circuit boards. Securing the communication microcircuit using microscopic specialized screws. Tightening with just enough force to avoid cracking the board. Taking the new screen glass from the vacuum-sealed plastic bag. Preparing for assembly. Tearing off the protective anti-scratch plastic film. Carefully fitting the LCD panel precisely into the groove of the plastic frame, carefully smoothing out the ribbon cable to avoid sharp folds. Installing the carbon membrane directional button cable module into the correct slot position. This is the button cluster for tweaking shooting parameters. Attaching the front plastic cover and battery tray to the internal load-bearing structure. Connecting the power module to the optical assembly. Ensuring the gold-plated contact spring poles sit correctly in their alignment slots. Fastening the screws to secure the battery frame, using a soldering iron to resolder the electrical wires, supplying main power to the device, adding more solder to create a solid joint, soldering the tiny microphone cables in place, and the anti-interference grounding points, red wire to positive, black wire to negative, sliding the FPC ribbon cable of the optical sensor into the ZIF socket on the motherboard, extremely carefully, to avoid breaking the copper pins, using tweezers to press down firmly on the locking latch, locking the image signal contacts firmly, ensuring stable transmission of image data, skillfully inserting the ultra-wide-angle Zeiss lens module into the microprocessor frame. The 2 core components have been unified, using tweezers to reroute the audio signal cables, which are extremely fragile, tucking the cables neatly into the routing grooves along the body. Placing the white reinforced structural frame on the side, and pressing the latches firmly, aligning the subboard tightly into its slot, tightening the frame positioning screws, to form a solid mechanical unit. The camera has taken shape after the reconstruction process, slowly sliding the entire core engine block inside the white outer shell. It fits perfectly thanks to the original shell. Installing the tail cover containing the steel thread mount for a standard 1/4 inch tripod. Inserting screws to secure the bottom base plate, installing the carbon membrane button cluster, and attaching the protective side cover for the display screen. You're engaging the hinge pin of the protective door, finishing by screwing the protective bottom cover shut, closing the latch of the battery cover and I/O ports, securing the side plastic cover wrapping around the screen, testing the mechanical click of the multi-function video record button, placing the soft rubber button strip on top of the camera, applying the acrylic mica glass to protect the secondary display, preparing sterile medical cotton for optical procedures, tearing a thin layer of cotton to clean the lens, using a sharp metal pick to pry around the lens edge. The original Sony protection ring is completely shattered, applying a little solvent chemical around the edge, breaking down the industrial glue holding the old lens. The solvent reacts, weakening the glass bond. The optical coating is scratched and clouded, beyond repair. Getting started on recreating a new protection ring, using an epoxy compound, specialized epoxy part putty, using a spatula to scoop equal amounts of both compounds, base, and hardener, which need to be mixed well to trigger the curing reaction, using fingers to knead and mix the epoxy block. On the aluminum tray, body temperature will accelerate the chemical curing process. 2. Roll the mixture into a long, evenly thin cylindrical strip, ready to be applied to the frame around the face. Lens module. Tray. 4. Bend the epoxy strip around the protruding lens mount. This material will cure and harden like solid plastic after a few hours. Gently smooth it with a fingertip so the glue adheres tightly to the housing, shaping a raised cylindrical form, replicating the design of the original bezel. 1. Use a metal tool to meticulously press and shape the curve of the bezel, ensuring an even thickness that doesn't obstruct the sensor's field of view. 2. 1. Trim the excess glue using ultra-fine pointed tweezers, creating a perfectly curved bevel that fits snugly against the glass edge. 2. Rub the glue surface with a damp cloth to smooth out any bumps, creating an aesthetically pleasing matte finish before the epoxy block fully hardens. 3. Now, hook a heated soldering iron into the groove to pry the lens, separating the shattered glass from the optical sensor chamber. The damaged glass is removed, freeing up space for the new component. Preparing to sand and refine the newly created bezel. The glue has hardened. Use ultra-fine sandpaper to polish the ring. Consistent friction makes the epoxy surface flawlessly smooth. 4. Continue folding the sandpaper small to polish the tricky rounded corners. Meticulousness will determine the aesthetic appeal of the FIDE. Front camera module. Using a specialized car surface polishing cream, Car Cream. This compound helps remove tiny stains and scratches, and creates a glossy finish. Using a microfiber cloth wrapped around a finger, rub the cream onto the protective ring. The applied ring section, made of epoxy, now perfectly matches the body's color. 1. Wipe clean. The residual polishing cream on the polycarbonate shell. An incredible revival. The shiny Sony looks just like new. 2. Peel off the sterile packaging of a transparent protective lens. A beveled glass lens. A perfect replacement for the original part. 3. 1. Remove the ultra-sticky film and firmly press the lens into the glue-lined positioning groove. The mechanical mount and glue will completely seal the sensor inside. 2. Push the power button to boot it up. The microcircuit system has been revived. The side LCD screen flashes with the word "Wait." The power IC is working properly. 3. Synchronize the camera with the Live View remote. The wireless radio ING process via the Wi-Fi band is being established. Pairing successful. The color LCD screen displays the live recording interface. The BSI CMOS sensor has captured light, returning a sharp image, pointing the lens towards the flowers. The displayed colors are incredibly vibrant. The focusing capability is excellent, without any optical signal interference. Next, checking the optical response. In outdoor ambient lighting conditions, the Tessar lens and sensor are working in perfect harmony. The SteadyShot electronic image stabilization algorithm still stabilizes the frame excellently. The image shows no signs of distortion or bitrate degradation. Testing the function menu button combinations on the remote accessory, the navigation interface changes smoothly, with instant feedback. A close-up of the monochrome LED screen clearly shows the standard Wi-Fi connection status. The duo of devices that were once buried in the mud have now been completely reborn. Static camera angle. Admiring the housing surface and the epoxy-filled bezel again. No one would believe that. It was once a piece of scrap lying in a junkyard. That is the magic of advanced microelectronic component restoration techniques. A legendary 4K action cam from Sony has made a glorious return.